So a pleasure to be here. Thanks for the organizers. Great collection of people and projects and ideas. We're going to tag team this a little bit too, but it'll probably be just a little bit more integrated as a single project. I'm going to start out just motivating where this project came from, and then Mike will talk a lot more about kind of what it is and where it's headed. This project started with this initial motivation, which was sort of thinking about climate change and resilience in smallholder agriculture. But before you can think about adaptation to climate change, which I think is really it's a popular topic, you really have to start with smallholder farmers recognizing that something has changed. Right? You have to sort of start with that recognition that something is different before there's any kind of motivation to adapt, and that's partly because the adaptation process, adaptation to climate change, is a really tough stochastic dynamic programming problem for these smallholder farmers to solve, right? So when they change technologies, has to begin and end in their minds with their priors about climate and what climate is, the distributions from which their climate or their weather draws are being drawn. So how well do farmers detect climate change? How well or how quickly can they pick up on these changes? In psychology, there's a variety of perspectives on this question that may be useful. For starters, how people sort of in biased ways remember the past, how they can sort of formulate a statistical distribution on something by observing one draw each year from the distribution. And in smallholder agriculture, there's sort of an added challenge, which is sort of the inherent heterogeneity and stochasticity that it really defines smallholder agriculture. I mean, that introduces a lot of noise. It complicates social learning. And in work that we're doing also in Western Kenya, we see just how big of a barrier to learning heterogeneity in soil characteristics, for example, can be. And farmers realize it. If they're in a village that is very heterogeneous in fertility measures, they're much less likely to learn from neighbors. Right? So this is a really tough learning proposition. This is just sort of a pedagogical tool to sort of reinforce this point. If you think of this, you can see a farmer there in the Andean highlands, a potato farmer who looks up each day at the glaciers in the Andean highlands. I mean, he's actually in a much better position to track long-term changes because the glacier is the memory, right? The glacier has the memory, so Kilimanjaro, same thing. Those in Kenya and Tanzania that look up, they see the memory that is changes over time that otherwise are hard to perceive. So we're looking at a case, we're motivated originally by this case in Morocco where the climate actually did change quite dramatically in the early 80s. So here's a snapshot of that change. So this is, in blue here is rainfall, in red is temperature, measured in sort of the breadbasket of Morocco near Meknes. And you see around 1981-82, there's this kind of strong statistical structural break in precipitation patterns. It goes from an average of about 600 millimeters a year down to 430 millimeters a year. So this is actually due to this North Atlantic oscillation that is sort of well known, sort of a much longer lived cycle than El Nino. But what's interesting here is it gives us a chance to sort of think about how long does it take farmers to actually detect this change in the distribution, right? Because year on year, there's still good years and still bad years. How long does it take to pick up that change? So that's the question that really motivated us initially, was trying to construct sort of ex post, looking at this episode, what is sort of the learning process for a change, a very discrete, something we can pick up statistically as a very discrete and sudden change. And that led us to really thinking about what you can do with landscape level data to construct outcome variables that capture something about farmer level decision making. Okay? And because we started there, we're actually looking back to sort of Landsat days and beyond, trying to think about how you process those data to generate landscape level outcomes. And this is the basic motivating question for this project, is can we track at sort of a decent spatial and temporal resolution, track the diffusion of irrigation in agriculture? There's a whole that sort of beyond the motivating question that I just mentioned, I think there's a lot of other things that we could do with this kind of sensing technology. So, and that's mainly because irrigation in smallholder agriculture is such an essential part of resilience. It defines resilience in many of these cases. So how do you think about resilience? How do you think about responses to drought and drought vulnerability? Well, thinking about over the course of many years how irrigation, small-scale and large-scale irrigation, has diffused across the landscape, I mean, that has a lot of implications for how you think about the effects of drought on food production, on food markets, on vulnerability and food security among smallholder producers. That includes actually, I'll say this and then hand it over, that includes sort of both sides. So we're actually, in Morocco and in many countries in the last 30 or 40 years, this was a time where access to irrigation has sort of increased almost monotonically year on year. Big infrastructure projects, canalization, reservoirs. And so thinking about how those large-scale projects sort of diffuse into small-scale irrigation and how that changes cropping patterns, I think already is interesting. We're in a situation now in places, for example, in Northeast India, as David talked about. We have a couple projects there where groundwater depletion is severe enough and water tables are falling fast enough that we may actually start seeing sort of reversal of this kind of monotonic increase in access to irrigation, right? And there the reverse question, I think, becomes very important when you think about resilience. So which are the plots and which are the farmers and which are the villages where irrigation goes offline first? What does that diffusion look like? Sort of the retreat of irrigation in landscapes that are now water scarce. So that sort of sets the stage for what we're hoping to do. Mike, why don't he'll talk a bit more about the methods that we're using to get at that question.
All right. Thank you, Travis. Yeah, so we started with that research question of trying to figure out where irrigation was at which time. So I started doing a lot of research into what already existed out there. And a lot of the existing land-covered data sets don't distinguish between irrigated and rain-fed cropland. You look into it, it just looks like cropland. There were a couple more promising leads, the Moroccan Agricultural Atlas and the FAO Aquastat files. They had their own problems, which I can get into if you want, but at best they are just snapshots of what was happening at a particular time. So you look at this land cover change detection strategies, and in 2008 this Landsat archive became freely available to everyone. So if you look at academic papers from about 10 years ago, they often just looked at 2 scenes or 3 scenes because they had to buy each one and differentiating between the two. And now we can use them all and start looking at differences on a continuous basis using tools like Google Earth Engine, which has the processing power to do this. So it's an exciting time to start looking at these changes. And I should mention there are some very sophisticated models for detecting irrigation using evapotranspiration, almost like an engineering standpoint, using these water balance and heat surface flux measurements. Again, it's very data intensive, it's computationally intensive, and you need a lot of information to get that snapshot at any given time. So what we've been doing, we've been working on an algorithm developed by Zhu and Woodcock, came out in Remote Sensing of Environment last year, where they fit this sine-cosine function using linear regression to the sensor data on an annual basis. So if you were just going to try and draw a line, as in the top left there, it wouldn't look very good. It wouldn't describe the patterns very well. But if you were to put in a trigonometric function, if you can remember back to high school trigonometry, you get this wave-like pattern which fits that seasonal green-up pattern of the crops. And so I started playing with this, and I was really astonished from a statistician's point of view that with this very simple model with just a few coefficients, you can get an R squared of 0.6 or 0.7, which is amazing to me that it would describe the data that well. As the method goes, you use the different Landsat bands as has come up in previous talks. There's different wavelengths of photons that you can measure, and the different types of land cover might show up differently in those different wavelengths. So you could distinguish between the land types based on the different bands, and then use an algorithm to help you with that. So in this image, this is from Morocco. This is what we were looking at. You have one rain-fed pixel and one irrigated pixel, and you notice there are a few differences between the two that we can pick up on. The seasonal pattern. In particular, I want to point out the year of 2007, 2008, where the rain-fed land never picked up that greenness because there was a drought, yet the irrigated land wasn't affected. So it makes a lot of sense that this would happen, right? Because the irrigated land is taking water potentially from a river where the water's coming from, the Atlas Mountains or something like that, or even pumping from an underground aquifer. So you don't really care how much rain there is. So the CCDC model as it exists right now doesn't take into account that contemporaneous information. So we wanted to include a measure of rainfall into that algorithm, into that wave-like pattern. And I won't get into the details too much, but you can develop drought indexes for telling you what is the availability of water at any given time. Like you have the US and you see where the dark spots are with drought. And I see people from California nodding. So you get something like this, where you have this wave-like pattern in the data that you can then condition based on the rainfall and take into account that drought in 2007. So the question is, we can throw a lot of data at it, but is it worthwhile to actually do this? Is it just extraneous information? So we looked at a few scenes from Morocco and tied in some of the existing irrigation data sets. On the top left there, I like that scene a lot because it has a very distinctive shape, the irrigation data set in green. And the blue indicates where the areas were very sensitive to that rainfall. And you can see outside the irrigated areas, most of it's very sensitive to rainfall. And you can still actually see the rainfall pixels from the remote sensing there with these blocky objects. And it may be that around the edges of that irrigation data set that we were given, it doesn't look like that's actually irrigated. And that polygon on the lower left there is very questionable, actually. So that green polygon is from a Moroccan government report that was then digitized. So how accurate that is, I don't know, but we're looking into it. And on the top right here, we have I'm going to butcher these names, but the Harb region. And that's characterized by having a river that runs through it and highlands on either side. And you can see the lowlands of the river where actually more rain hurts the greenness. You might consider that flooding or something like that. I'm not sure yet, but there seems to be a clear pattern there when you condition for rainfall spatially with what we know. So to conclude, the rainfall affects different types of agriculture differently, and we can exploit that pattern to distinguish the rain-fed and irrigated agriculture. It helps us understand the adaptation and learning dynamics of the farmers. And one important aspect of this technology is that we can monitor the water usage in real time. So hypothetically, each Landsat step is 16 days. So within 3 or 4 of those steps, you would know if the pattern has been broken. So if somebody's pumping water when they shouldn't be, and their plot's greener than it should be, you can pick up on that sort of pattern. Morocco is a great case study because it developed a lot of these dams and infrastructure over the past 30 years, but it's possible to duplicate this anywhere else in the world, especially with a tool like Google Earth Engine. And we still have some work to do algorithmically to get a little closer to the end results, but it's very promising. And thank you.